Okay, now we're cooking. All right. So, in any case, last time we were talking about how human beings solve problems in terms of memory, asking questions, and repetition, and that the job of a programming language is to attempt to mimic the way we already solve problems as human beings. Without us, and allow us to talk to a computer without us having to drop down to that computer's level, right? Because the real problem for us as programmers is that human beings are so good at solving problems that we have trouble articulating how we solve problems. So that programming language has to act as that middleman, that power tool that allows us to tell this computer what to do without changing our way of thinking too much. All right, so we talked about that there's a mapping. 100% of programming languages have this mapping between memory, emulating memory through variables, asking questions through conditionals, and repetition through loops, methods, or functions, that kind of stuff. We spent some time talking about some web technologies last time in terms of buzzwords, how JavaScript, Ajax, jQuery, Angular, React, these are all basically the same technologies, just evolutions of each other. They all do the same stuff. This is front-end web dynamic programming that, kind of starting with Ajax on, allows parts of a website to reload without the entire page reloading. We talked about things that are not programming languages, not that they're crappy or anything, just these don't match this model of supporting variables, conditionals, or repetition. Instead, these guys are data representation languages for modeling what a web page looks like and this kind of stuff. JSON and XML specifically are tools that that computer programs use to send information back and forth with each other, and that was something we kind of talked about afterwards. Last time we were talking about XML versus JSON. We looked at an example of a fraction in XML and a fraction in JSON. So if you had one computer program that wanted to send data to another computer program using XML and that data happened to be a fraction, it might send it in this format, whereas JSON, it might look in that format. Both of these are data representation languages. They're ways of organizing, structuring data so we can send from point A to point B. Let's see. So then we kind of talked about the web programming language technologies. We have the idea of a client and a server, where the client's the web browser, the server's the web server. The web browser is also called the client side or the front end. The server is called the server side or the back end. We talked about kind of where these languages fit and how these guys all work, Perl, PHP, Ruby. Talked about MIME types, how the server determines what kind of file is being requested and if it has to do anything to those files before it sends them on. But at the end of the day, all of these technologies are basically the same. Okay, so we talked about server-side, PHP on Apache, Ruby on Rails, Python on Flask, Node.js, which is effectively JavaScript on Node. These are all identical technologies. All right, so let's see. I wonder what we were talking about there. Well, it'll come to me at some point. Probably I jumped here for some example for a question that was asked. But in any case, this looks like it was a Node.js. Yeah. This is number crunching thread and IO thread. So we talked about Node.js kind of leveraging itself for being scalable, and this is just a model that it kind of used. So you can reference last week's video if you want to see see the details of that. But that's what we were talking about there. Okay. So now we've been kind of using, this is kind of our governing chart for this workshop that we built last time. We're going to be using this time. So last time we pretty much dealt with all these things over here. These are all of our web languages, but we're going to give some. So these are our web languages, and then these guys over here are our native languages. All right. Now, in order to give a little bit of kind of structure to what kinds of languages exist out there, before we jump into the evolution of C and C++ and those guys, I want to kind of generate a couple of slides here that all have kind of the same heading, but look at languages from a couple different angles. All right, so one thing I like to say is, so there are three kinds of programming languages. Okay, we have machine language, we have low level, and we have high level. Okay, now machine language, these are our zeros and ones. Okay, not for human consumption. None of us would do very well with the little 2-button keyboard floating around out there and us just tapping out zeros and ones all day long. So we need something at least a higher level than that. All right, so this is where this low-level language comes in. So a low-level language has a one-to-one relationship with the CPU. And I'll talk about what that means here in a second. A high-level language has a one-to-many relationship with the CPU. All right, so in order to understand what those things mean, we have to understand what the CPU is. All right, and this is where things start getting interesting. Many technologists, especially programmers, think they know what the CPU is, but unfortunately most do not. And this is kind of the problem. It kind of all wraps into what we talked about last time with buzzwords and things like that, where we take for granted these words that float around and we think we know what they mean. We think we understand the nature of that beast, but we really don't. So, you know, if I ask somebody what a CPU is, you know, what's the obvious thing that comes out? Well, they say it's the central processing unit. Okay, well, what does that mean? Okay, well, it's, you know, sometimes people say it's the brain of the computer, okay, or something like that. And that might be true, okay, but what does the CPU actually do? It's this resource. It's a little machine inside of our computer that is trying to solve a problem. All right, so now the CPU itself, I like to think of the CPU as a magician that can do a bunch of magic tricks. And if enough magic tricks are done in a certain order, a real problem can be solved. So at its core, a CPU is essentially a hardware version of a whole bunch of little functions or procedures or methods, however you want to think about it. It's really a computer program that's been turned into hardware for performance, for speed. But there's just a whole bunch of little tiny things that do something on the CPU. Now, one of the problems with the CPU is each magic trick needs to be granular enough to solve a real problem, but not too big to solve too much of a problem, then requiring us to have to kind of roll back. All right, so there's this weird like balancing act that like Intel and AMD need to solve when they're designing these processors. They need to create minimalistic functions on this processor, minimalistic magic tricks as I refer to them, that allow us to solve a grand classification of problems with our programming languages, but each of those magic tricks needs to be granular enough to kind of be compatible in all sorts of different other magic tricks, but not too big that they solve too much of a problem where they become useless in other magic tricks. All right, so it's kind of a weird balancing act. But in any case, if we think about a CPU as basically being a collection of little magic tricks where we say, okay, perform magic trick 1, then perform magic trick 8, then perform magic trick 13, then perform magic trick 4, and that is supposed to accomplish something real, that's how we want to think about our CPUs. Now, when we get back to this slide about our different languages, a low-level language has a one-to-one relationship with the CPU. That means every line of code we write in a low-level language translates into exactly one line of code, one magic trick on the CPU. And the way I like to kind of explain this, if you haven't seen it before, I'm going to bring up an example of a assembly language program. Let me just find the one I like to use so that will work. All right, and let me share a different screen here. I'm going to kind of walk through an example of a hello world program in a low-level language. This is Linux assembly language that we're looking at right here. Okay, so remember the previous slide we looked at talked about that a low-level language has a one-to-one relationship with the CPU, where a high-level language has a one-to-many relationship with the CPU. So every line of code we write in a high-level language translates into a whole bunch of magic tricks, or a whole bunch of lines of code in a low-level language. All right, so if we were writing hello world in Java or Python, or pick your favorite high-level language, it's one line of code. System.out.println hello world, print hello world, whatever it is, something like that. Well, this is hello world in a low-level language. So I'm going to kind of walk through this and kind of tell you how this works, so we gain kind of an appreciation for how all of our high-level languages ultimately get turned into something like this. And this is actually what the CPU feeds off of. Okay, these instructions, the CPU, we say do this magic trick, then this magic trick, then this magic trick. So this is kind of under the hood mechanics stuff. All right, so as we kind of look through this, we have, this is just gibberish up here. We talk about there's a text section, and then there's a global start. This is where the program begins, is in the start section. So that's it. That's this part right down here. And then we have a data section at the bottom. That's where our variables are originally defined. So we have two variables here. One's called message, and its value is hello world. The other one's called len. That's the length of that message. So leave it at that. That's kind of how we would define stuff here. This is end of string character in this language. But we really care about this stuff right here. These are the magic tricks that we are issuing to the CPU and to tell the CPU what to do. Okay. So first of all, let's introduce the players in our little scene here. We have this thing called EDX, ECX, EBX, and EAX. These guys are what are known as hardware registers. These are little variables made of hardware that live on the CPU. Really, 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 really fast, really, 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 really expensive, and really, 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 really small. All right, but in any case, we use those as staging areas for values during the run of a low-level language, a low-level program. All right, this is the move command. So we're moving this value into this hardware register. So what do we do first? We move the length of the string into EDX. We move the string itself into ECX. Then we move the number 1 into EBX. And the number 1 represents where we're going to be writing our hello world out to, which is going to be standard output on the monitor. Then we move the number 4 into EAX. What is that? That references the system call syswrite. So this is a function name that's supported by the Linux operating system. All right. So the syswrite function requires 3 inputs. It requires the output stream we're going to be writing to, the string we're going to be writing, and how long what we're writing is going to be. 3 different inputs for this particular guy. So we've staged these 4 values in 4 different hardware registers, and then right here we interrupt the CPU and call upon the kernel. So the kernel is the actual operating system, and the kernel is going to first look here and see, oh, you want to do a syswrite. Great. I expect that you've already filled in the other 3 memory addresses, the other 3 hardware registers. So I'll go ahead and figure out where you want me to display this, what you want me to display, and how many characters it has in it. I'll go ahead and do that for you. Then we'll come back to the program. What does the program do next? Notice it's loading into EAX, the number 1, which is the sysexit system call. So we use EAX for system calls. Every single time we use EAX for system calls. It just so happens that the sysexit system call, that function doesn't require any extra inputs. So that's why we didn't preload anything else. So then when we interrupt the CPU and have the operating system take over, it's going to look in EAX, say, oh, you want to exit? It's going to flag the process that was just running on the CPU as being done. The program's done, it's over, it's finished running, blah, blah, blah. It's going to go and die somewhere. Okay? Now, what we're looking at here should look relatively complex to us, but at the same time, it should feel like it's plausible for a human being to have written that program. That's kind of the important thing for us. All right, so let me go back to the presentation deal here. Okay. So that's a low-level language. High-level languages, these are our friends. So these are our languages like Python or Java or C or C++ or C# or Swift, Ruby, PHP, all these languages are high-level languages. So every line of code we write in a high-level language translates into many, many, many magic tricks on the CPU. So it's a power tool for us so that we don't have to get to that granular level, which would be very tedious for us as human beings. Okay? So that's one way of looking at programming languages, 3 different kinds of them. Next, there are 2 kinds of programming languages. We have interpreted languages and we have compiled languages. We like to think of interpretive languages as being relatively slow and compiled languages as being relatively fast. Okay? So we might say, well, why would we ever want a slow language? Well, notice I've used the word relatively there. Our computers are pretty fast. Therefore, even the slower language is going to feel real-time to a human being. Interpreted languages are often much, much easier to create. This is why you often see, well, whenever a new programming language comes out, it's more often than not an interpreted language. So languages like Python and Ruby and PHP, these are all interpreted languages because they're written on top of, they're written using an existing compiled language. So a Python interpreter was created in C, which runs on the computer and can understand Python. Okay? Now then you have your compiled languages, which are relatively fast. We mainly use these for video games and that kind of stuff, where our interpreted languages are plenty fast for business applications or websites and things like this. Compiled language is also for operating systems. So anytime that a program really does have to be very, 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 very fast and giving up any performance isn't acceptable, we would use a compiled language. Otherwise, we'd use an interpreted language. Now, why are they slower or faster? Well, let's talk about a compiler. What's the job of a compiler? Well, we can answer this in terms of what we saw a couple slides ago. A compiler translates from a high-level language to a low-level language. All right, so we might take, if we were using Python for, actually Python's an interpreted language, let's say we're using Java. So in Java, if I type in, I'm on a Linux machine, I type in system.out.println hello world, and I run it through the Java compiler, it might turn it into that assembly program we looked at a few minutes ago. That would be the output of the compiler after we compiled our high-level program that just had that one line of code in it. Okay, so that's what a compiler does. Now, it's relatively fast because what it does is all this, so this translation, this happens prior to runtime. All right, so, you know, the real life example of this is, let's say somebody important is giving a speech, and the speech is being delivered in English, and there's a German news station that wants to carry the speech. Well, the compiled version of that is they're going to receive the speech an hour ahead of time, and their interpreter is going to convert the speech from English into German so that when the speech is going on live in English, the German news station can be delivering the same speech already converted to German with no delay. Okay, that's a compiled language because we did the translation ahead of the speech actually running. Okay? Now, an interpreter is the opposite of that. This converts a high-level language to a low-level language during runtime. All right, so this would be equivalent to that German news station having an interpreter who's going to be listening to the English speech as it's being delivered, and with a couple of second delay, translating the English words into the equivalent German words. It's going to be sufficient for most applications, but maybe not fast enough for some. Something along those lines. So that's kind of the difference between those two languages. Is interpreted languages are relatively slow, compiled languages are relatively fast. With that speed also comes some complexity. So that's a fair enough thing to say. Okay, so let's see. There are two kinds of programming languages. We have loosely typed and we have strongly typed. Loosely typed are relatively slow. Strongly typed are relatively fast. Okay, these are relatively fast. We might also throw in here that loosely typed languages tend to be interpreted languages, and strongly typed languages tend to be compiled languages. So these things all go kind of hand in hand. And if we can, as a programmer, if we can look at the language we intend to work with, and if we can kind of compartmentalize it into the type of language it is, what kind of animal that guy is actually going to be, then what we can do is we can actually make some decent guesses of how that language is likely going to act. Okay, and that's going to be related to what we're about to talk with when we talk about our evolution of our programming languages. Right? Pretty much everything we talked about last time are loosely typed interpreted languages. So all of these guys, Perl, PHP, Ruby, Python, Node, all of those guys are high-level, loosely typed, interpreted programming languages. Okay? That's what those guys are. So now we want to look at these guys over here. So if we just kind of fill out the slide a little more, we can say these are all high-level, loosely typed, interpreted languages. That's what all those guys are. These guys over here are high-level, strongly typed, compiled languages. So we could also throw a final line here and say slow and fast. And again, those are all relative terms in our world here. Okay, so kind of going along those lines, let's kind of keep kicking here. So what I'm going to do is I'm going to drop down. We're going to start talking about the evolution of these different languages. How did we go from the top of this tree, from C, all the way down this trunk, and then how were these guys born from that? I already led you into that a little bit by saying, like, for instance, the Python interpreter is written in C. So we really needed to have this guy before we could write this guy. But these languages, which are often called scripting languages or web languages, are often considered to be simpler programming languages, but they're not really simpler. Programming as a skill set is still what we need to apply these languages, but the cost is that since these languages are written in terms of a pre-existing language, they're able to kind of abstract some of the complexities of the underlying language and make things maybe a little bit more of a power tool for the underlying user at the cost of some performance. Okay? So maybe that's something to kind of consider. Okay, so let's kind of dive into evolution of C. I like to look at C through the lens of this very first thing on our list here, and that's memory. This guy right here. So I like to look at C through memory or variables, because I think that's really where we see C evolve and then ultimately kind of go away on us a little bit. All right, so what did C support? C supported a variable, which is a single name with a single value. C supported an array, so this is a single name with a collection of like values. All right, and we kind of have a more recent relative of this guy. If you're one of the loosely typed language developers in Ruby or Python, this is a list. All right, they're called arrays in our strongly typed language. There's some structural differences there, but you know, that's that little connection. All right, the list would be an abstraction of array. So we have a variable, we have an array, we have something called a struct. All right, and a struct is a single name with a collection of name-value pairs where the values are not necessarily alike. All right, and for those of you web programmers out there, I'm going to just say this is kind of like a dictionary. There's something we're going to be talking about here that is very, very important for us to understand. That's a major difference between our, kind of our languages, and we need to understand this concept. So a struct isn't quite exactly like a dictionary, and the punchline will come here in a few minutes. It's just not time yet. All right, so having said that, this is kind of where C stopped. All right, so C is a language from 1968. I don't remember if I put that on our chart up here, but this is a pretty old language up here. So 1968. All right, and so there's some things we need to consider with C and try to understand about why C kind of fizzled out for us, and also why C made some of the decisions that it made. The first thing I like to do, specifically with C, is I like to look at C's primitive types. Okay, so again, this is talking about variables in C. We talk about the built-in variable types that were built into the language C. So we had the byte type, we had a short, we had an int, a long, a char, a float, a double, a bool, was like that, Boolean type. We'll leave it at that for right now. All right, so what are these guys? Okay, what are these types? Well, a byte holds whole integers. A short holds whole integers. An int holds whole integers. A long holds whole integers. A char holds whole integers. All right, so first of all, right off the bat, we have 5 different variable types, all built for holding the same crap. All right, so why is this? Well, we got to give a little bit more definition to these various values. So C came in 1968. And what we need to understand, we need to put ourselves in a mindset. And this is one of the biggest things that young programmers today miss. Okay, they don't see this because they didn't live through that time period. They don't have an appreciation for that time period. So I'm gonna even take it much more recent than that. So, let's think about our computer. So in 1996, I had a computer. It was a 486 DX2 66 megahertz computer, and that computer came with 8 megabytes of RAM. All right, and I decided, as a cool kid, that I was going to double the RAM a year later. Not even a year later, but something like that. I wanted to get another 8 megabyte chip. Not gigabytes, megabytes. So in 1996, an 8 megabyte chip cost about $1,000. Okay, $1,000. Today, well, we don't think about things in terms of megabytes anymore. Today, you can get a 8 gigabyte chip for about $40. Okay, and 1 gigabyte is 1,024 megabytes. So 8 times 1,024 is 8192. So this is actually 8,192 megabytes for $40 today. A lot cheaper. A lot cheaper. And also a lot faster. So punchline here is, back then, today we don't view memory as being a problem. Okay, memory is very inexpensive today. If you want to double the RAM in your computer, $50, $60, even if you're paying retail at Best Buy or something, your RAM is doubled in your computer, no big deal. It used to be cost prohibitive. So you got to imagine that languages that were developed during a time when that was something to consider had to take that into consideration. So in C, a byte holds positive or negative, so we'll just say plus or minus 8-bit numbers. So that's negative 128 to positive 127. That's the range of values we can fit inside of a byte. A short was 16 bits. that's negative, what's it, negative 32,768 to positive 32,767. And int is 32 bits. All right, and this is roughly negative 2.1 billion to positive 2.1 billion. And then a long is 64 bits. And this is negative, I think it's 16 quintillion to positive 16 quintillion. Don't quote me on that, but it's plus or minus 2 to the 63rd power. You can quote me on that. All right, because one of those bits is used for the sign to hold the positive or negative. So the other 63 bits are for the value. So this will be plus or minus 2 to the 63rd power. The other one, next one up, will be 2 to the 31st, 2 to the 15th, 2 to the 7th. All right, that's where those numbers came from. All right, so we, as a programmer back then, we had to really consider what kind of value, what kind of variable we should use to hold the value based on what the maximum size that value could be, or the minimum size that value can be on the negative side. All right, so we had a whole nother range of decision making that we needed to make as a programmer. Okay, today, especially with our loosely typed languages where we don't get to choose the type. In our loosely typed languages, we just create a variable, we put something into it. No harm, no foul. And let the language decide for us. Those languages are able to abstract that decision making away from us because memory is no longer a problem. They could just always store everything in an integer, and if that's not big enough, throw it in a long or something like that. All right, so and then beyond that, they can have object structures for holding even larger arbitrary size values. So the thought process of a programmer has changed, and we had languages that had to support it. Similarly, and this gets back to that whole machine language slide from a few minutes ago where computers understand zeros and ones, when we think about a character, we're thinking about A's and B's and C's and question marks and things like that. Well, in an old language like C, these guys were actually 8-bit unsigned numbers. So that was 0 to 60, actually no, 0 to 255. 0 to 255 was the range of values that we could store in a char, and this just happened to match up to the American Standard Code for Information Interchange, which is just a mapping lookup that says this character, this number represents this character, this other number represents this character, so on and so forth. So binary numbers, 8-bit binary numbers mapped to some character in the ASCII character set. Computers like numbers, human beings like characters. That's the punchline there. All right, more modern versions of C and C++, like for instance Java, chars are 16-bit unsigned, so it's 0 to 65,535, and that's the Unicode character set that it maps to. So there's a little evolutionary step in there because at some point in there we realized that not everybody in the world uses the English character set. So the Unicode character set supports symbols from languages all around the world, not just English. All right, floats. A float is like a int, but can hold decimal numbers. And a double is like a long, but can hold decimal numbers. It's a little bit more complicated than that. A float has a certain number of, I think a float is 48 bits, so that's 32 bits before the decimal point and 16 bits after. And a double is 96 bits, I believe, 64 before, 32 after. So just for holding footprints of values. And a Boolean is true or false. Back in the older language, it was 0 or 1. Now it's been abstracted to trues or falses. Doesn't really matter in our world here. We just kind of really wanted to understand this idea of the size of those numbers. Okay? And we've actually all experienced, or maybe have all heard of something that was very much part of this. and that's the Y2K bug. All right, so most of us have probably heard of the Y2K bug, but depending on your age, you may or may not know what it actually is. It's just something that's a buzzword that's floating in there somewhere. So the Y2K bug came around as we were getting near the year 2000, so about almost 16 years ago. So what was the deal with it? Well, we had a whole slew of computer programs around the world at that point. You know, computers were running the world already. We have programs all over the place, and these programs had been written prior to the year 2000. Now remember, a few slides ago, I talked about how expensive memory was in 1996. Now, memory was still fairly expensive in 1998, 1999, so on and so forth, but that was right around the period where things started dropping drastically. Memory was becoming significantly more cost effective. Now, with that in mind, many programs that we were using that in the late 90s were programs that had been written significantly before that. And those programs were written during a time period where memory was at a premium. Memory was very expensive, where developers had to decide how big of values do we use to hold our memory. Okay, now this is where the kicker comes in. So developers made the decision, you know what, we're going to hold the year for our, in a date field. We're going to hold the year as a 2-digit year instead of a 4-digit year. So instead of 1999, it would just be 99. And then when it got to the year 2000, it would be 00. And all of a sudden our programs weren't going to be able to differentiate between the year 1900 and the year 2000. All right, so the idea here is that all of a sudden people started freaking out. You know, is the electricity grid going to go down, or we've become so dependent on computers at that point in time, yet we kind of forgot how reliant we were and how everything's going to change now, since certain things are going to break because the sorting of dates is going to be broken. All of a sudden yesterday should actually come after today, because today is 1900 instead of 2000. So kind of a weird fiasco. So there was a big movement to try to update a whole bunch of software, and that was the Y2K bug. And I remember sitting on my couch as it was hitting midnight in all these different places. All the cameras they just had putting on like the power stations and just seeing if we saw sparks and stuff like that. And I can tell you it was very much underwhelming. I spent about 14 hours straight watching, basically watching nothing happen. But in any case, that's the Y2K bug. But you know what we want to so kind of getting back to this evolution of C thing here. What we want to understand is that C was and still is a very good programming language. Okay, but it had some weaknesses. And the weaknesses didn't have to do with the memory stuff. Okay, C had tools that allowed the programmer to decide how they wanted to handle memory. So any programs that came out that were written in C that were written poorly because of memory, that was the programmer's fault, not the language's fault. Okay, but really the sticking point is here with these things called structs. Now, we talked last time about how the job of a programming language is to help a human being solve problems similarly to the way we solve problems in real life. And then last time we also talked about object-oriented. I think we actually we didn't. Oh, that's coming up to our punchline. Okay, good. So the way we solve problems in real life, that's the job of our programming languages. Now, I think we all can agree that 20 years ago, 30 years ago, when computers were very young, the types of problems we solved with our languages were much simpler than the types of problems we solve today. Similarly, our computers 20 or 30 years ago were significantly less powerful than our computers are today. So as the computers got more powerful, and as our reliance on those computers became more and more, and as human ingenuity and we started inventing new ways of using these computers to make our lives easier, we started requiring more and more from our programming languages, to the point that C was making it very difficult for us to continue to innovate without our languages becoming our programs becoming very messy. Okay? And the big reason for that is this idea of a struct. So we mentioned that a struct is a single name with a collection of name-value pairs, but the values don't have to necessarily be the same. And let me kind of show you an example of a struct. So I'll just create a little text thing here, and we'll stick with our fraction example from, actually let's make it a person. That way we can have a couple different types. So I'll say person P, or actually we're going to say struct person. And we're going to say that we have a string name and we have an int age. Good enough. All right, so that's the pieces of information we're going to hold inside of a struct. That's a structure. So a person structure is going to keep track of various attributes associated with a person, and our little simple person we've created here keeps track of a name and an age. Okay, so having said that, now we can create a variable of type person. So we'll say person P, then we'll say p.name is equal to Mike, p.age is equal to 15, if you believe that. All right, so there's our a use of our struct. Now, the catch here is structs were good when we just needed to store pieces of information about a single kind of value. So XY coordinates, stuff like that. But the second we started trying to manipulate those types of values, okay, working with the name and the age and things like that, we started wanting to have functions that operated on the name and the age of these guys. And structs did not support the embedding of functions. So we could not come inside a struct here and put a function in here. We couldn't say we wanted to display person and then have this guy print out the information about that person to the screen, knowing what the name and the age was. Instead, what we would have to do is we'd have to take that function and we'd have to write it externally to this. So maybe display person took in a person P as a parameter, and then it would, back then it would have been printf. So we say %s, %d, p.name, p.age, something like that. All right, and that would print out that information, but we would have to provide it with the struct, first of all, but also the function would have lived outside of the structure itself. So we kind of held the wires laying all over the place, if you will. I'll kind of close this gap here in a second when I kind of talk about evolution of C++ and object-oriented languages, because this idea of object-oriented programming is more of a buzzword today. We don't. When I ask somebody what makes a language object-oriented, it's very hard for them to describe, and I can't necessarily always tell, is it because they don't know or just because it's a kind of a weird concept. But I'm going to attempt to explain it in hopefully a pretty simple way for you today. But in any case, we're going to say that from a C programmer's perspective, as the programs that we were trying to write were getting more and more complex, we're going to say that this was becoming a problem. We couldn't keep all of our stuff inside of a struct. We couldn't keep everything that we really wanted inside of the struct. And we actually got to the point where programmers started trying to hack it. So they were coming up with like weird void pointers. So we have a void pointer display func or something like that, where you'd actually have a variable which pointed to the memory address where an actual function lived to sort of kind of fake having the function being inside of the struct. Very strange, and it was kind of a call for help, a cry for help, if you will. All right, so having said that, I'm going to go ahead and steal the evolution of C slide, and we're going to say evolution of C++. All right, so evolution of C++, what did we do? Well, we kept the variables, we kept the arrays, we kept the structs, but we added a new guy called a class. And what's a class? A class is a struct. Well, let's say it's like a struct. We'll see Java's mistake here in a few minutes. So a class is like a struct, but it can also hold functions. That's what a class is. It's like a struct, but can also hold functions. All right, so now what we can do is we go back to this slide and we switch this struct over to a class. I'll just shrink this down as well. So now I can say class person. Whoa, that was a couple of keys off there. And then we can take this function and we can suck it into the class itself. All right, this guy would have returned a void, and oh, well, now we're dealing with C++, so it's no longer printf, now it's cout. I'll just leave it as printf, just let me get away with it. All right, so in any case, you know, you get to move the function inside the class now. So now what you can do is you can just say p.displayPerson, and it will go ahead and be able to display the stuff. So it's an organizational tool. Okay, and again, remember that the job of a programming language is to emulate the way human beings already solve problems. And to kind of put that into perspective, let's talk about procedural versus object-oriented, OOP. Because C was a procedural language. C++ is an object-oriented language. And I like to talk about this from the perspective of a telephone. The procedural telephone is a pile of wires where all of the details are exposed. All right, so if you walk into a room and on the table I have a giant pile of wires and I tell you that this is a telephone and you think I'm full of it, you come up and you inspect it and you look around, you find kind of some of the buttons, you pick up the handset, you hear the dial tone as if that exists anymore. But finally you're convinced that in fact, even though it doesn't look to us like it's a telephone, it is in fact a telephone. An ugly one, but a telephone nonetheless. All right, so that's the procedural telephone. The object-oriented telephone looks like a telephone. That is, all of those wires are stuffed into a telephone-shaped box. And only the public interfaces, that is, only the parts of the telephone that we actually have to commonly interact with, the buttons, the handset, those things, are exposed. That's the object-oriented telephone. And what's that telephone-shaped box called? That guy's called a class. All right? So what's the difference between a procedural language and an object-oriented language? It's a piece of Tupperware. It's a container that we can stuff all of our toys in from the C language and poke a few holes into it and only expose the things that we actually are going to commonly have to work with. You know, we all believe that inside that telephone there's a zillion wires and things like that, and something could potentially go wrong, and some smart person put it all together at some point. And we know that if something breaks in our phone, if we were really, really interested, we could crack it open and get in there with a soldering iron and see what kind of damage we could do. But chances are we're going to run out to Target and buy a new phone. All right, so the punchline is that what we need out of our real-life objects is we need them to function, and we understand there's complexities inside them that had to be put into place to make them function. Somebody built the telephone, okay? Just like in our computer programming world, the programmers are going to have to write those complexities. But what we can do then is we can shove those complexities inside of that telephone-shaped box, or whatever the object we're creating is. We can shove those complexities in there and then pass that object around, pass that box around, and only expose the parts of it that we actually need for solving the problem. A telephone is built for making phone calls. Okay, so even though at some point somebody had to sit down and make all those hard decisions and make all those wires and things like that, once it works, we just make telephone calls on it, or we do text messaging and all this other jazz. All right, so that's the difference between a procedural and an object-oriented programming. It was just a step of evolution, and at the end of the day, it was a Tupperware container. We just got a new container that knew how to hold name-value pairs as well as functions. That's it. Okay. So, having said that, what was the problem with C++? So C++ reigned supreme for a while. In fact, it's still very commonly used in video game design. For actually pretty much the reason that I'm going to say is the problem with this. So, the problem with C++ is it empowered the programmer to make dumb decisions. Okay, and this mostly applied to inexperienced programmers, beginning programmers. So, as an example, in the C++ language, well, let's go give you a real life example of something you could have pulled off in C++. So let's say that you're having a party tonight, and you're inviting your best bud Mike to your party. Do you give me the address to your house and tell me to be there at 8, or do you hand me your actual house and tell me to open the door at 8? Okay, it would never make sense to hand somebody a house because houses are heavy. So what do? You give me the address, you tell me what time I should be there, and I follow the address to wherever your house is, and I arrive at 8 p.m. As opposed to me standing there holding on to this gigantic house, just waiting for my turn to open the door. All right, so in C++, the language empowered the programmer to hand somebody the house, as opposed to give them the address of the house. There are certain circumstances where that never makes sense. In real life, it would never make sense for you to hand me the house. It always makes sense for you to give me the address of the house. In C++, the programmer gets to decide. Now, having said that, every now and then, a programmer might have a reason to do something like that in C++. And this has to do with this idea of side effect. All right, so we have two ways that values are passed around in our programming languages. We can pass a value by value, or we can pass a value by address. Okay, so let's kind of define these first so we can kind of understand where we go with these. So to pass something by address, what do? All right, passing the house by address is telling me where I can find that house. So if I give you the address to my house and you decide to drive over to my house and spray paint my garage, when I get home, I'm going to be in for a surprise, okay? Because passing something by address has side effect. If you change something at that address, there's side effect. All right, because I gave you the address to my house and you went to the real deal, the one and only Mike Littman house, and you spray painted my garage, now there's side effect, and I'm going to realize it when I get home. As opposed to this, let's say that you run up to me and ask to borrow a quarter, or have a quarter, let's say, okay? And I have 2 quarters in my pocket. I reach into my pocket, I pull out one of the quarters, and I hand it to you. In effect, I'm handing you a copy of a quarter. There's this mold known as a quarter, and there were zillions of copies of it made. I happen to have 2 copies. I gave you one of them. All right? So now you run off and you melt down that quarter. All right? So you melted it down for whatever reason, and the fact that you melted down the copy of the quarter I handed you had 0 impact on the other copy of the quarter I had in my pocket. Okay? That it has no side effect. So passing things by value means a copy is passed, and there is no side effect. All right, so that's pass by value versus pass by address. Now, sometimes passing something by address is desired. Other times, passing something by value is desired. Now, in C++, objects are always, well, let's go with a newer language. In Java, objects are always passed by address. In C++, objects can be passed by value or by address. So we used the example a few minutes ago of our house object. And that house object, if passed by value, is going to be very expensive. It would no longer have side effect, but in terms of the amount of memory that a house takes up, it's going to be costly. Okay? It weighs a lot. Now, every now and then, a programmer might say, you know what, I have an object that I've created, and I want that object to be passed by value. and let's say they're an experienced programmer and they have a good reason for this, whatever it is, they are empowered to make that decision in C++. In the next language, which we'll talk about next time, which is Java, that decision making is taken away from them. They no longer have that power, and we're going to see that that's a problem. Okay? Now, similarly, if we go back here to C++, classes are, let's write it in terms of typically passed by address. Structs are typically passed by value. Okay, and that's what I mean that structs, that a class is like a struct. It's almost the same thing as a struct, except classes are typically passed by address, whereas structs were typically passed by value. So now things sometimes have side effect or sometimes do not have side effect. All right, and just to kind of give us a quick jump start on next week, I'm going to copy this slide and I'm going to drop it all the way here to the bottom just so we can start down there. When we talk about the evolution of Java, we're going to see that we kept variables, we kept arrays, Java dumped structs, and kept classes. Okay? But they did this with the concept that isn't a struct basically a class without methods? Okay, that was really the premise that the Java folks were working off of. But we just introduced this idea that while they're very similar, technically structs were passed by value, classes were passed by address, so they're not actually the exact same thing. A class that doesn't have methods inside of it isn't identical to a struct. It's very similar to a struct. Okay, and this is actually the same reason why earlier I mentioned that structs are kind of like dictionaries in some of our loosely typed languages. Yeah, don't worry, I'll stop for questions here in a second. I just want to wrap up the thing so you can backtrack. It's not going to be a big deal. All right, so in any case, when I mentioned dictionaries back here in the evolution of C, let's see right here, and I said that structs are kind of like dictionaries. The difference is in C, structs are typically passed by value. In most of our modern languages, mostly interpreted languages like Python and Ruby that have dictionaries, these guys are all passed by address. So again, structs are similar to those, but not identical. Okay, so I'll go ahead and stop there for kind of the current lecture. We'll pick up from here next time, and we'll talk about Java and C# and how platform independence kind of works and all that stuff, and finally get into Swift and get our ultimate punchline of why the Swift programming language came out. Who is it trying to impress? Okay, so let's look at your question, then I'll take any other questions that folks have. Okay. Sorry if this question backtracks. How does scope work in a procedural language? Okay, well, sure. So, what is variable scope in general? Variable scope references where you have access to a variable. Or let's say where you can access a variable. So, you're trying to think about public, private, protected. You're saying, okay, well, it doesn't have public, private, protected. Well, procedural languages didn't need public, private, protected because they didn't have objects. So if we think about public, private, protected, what does public say? Public says every object can access this. Private says only things within this class have access. And protected, among other things, says that only things within this class or children of this class have access. Procedural languages we never got outside of the file you were currently sitting in. That you didn't have this idea of other classes. Okay, so the concept of public-private protected went out the window, and all we had was the idea of whether something was global or not. So I kind of like to draw a picture for scopes. So if we think about an original program, so almost think about if you were introduced to an object-oriented language. I'm going to do this, I'm going to do this, and I'm going to do this. So maybe we have a global variable up here. All right, and I'm going to create, so this is our global scope. So let's call this global scope. And inside this, maybe we have an int. Here, I'm going to left justify this too. Maybe we have an int a is equal to 5 in that global scope. We'll use C programming as our example here. All right, and then I'm going to put another scope inside of here. All right, I'm going to change the color of this dude. So this is going to be a red scope. He's going to be a little skinnier and a little shorter. All right, so this is like going to be a method. So local method scope, let's say. And let's say he has an int b is equal to 5. And then I'll steal this guy again, and we'll throw another guy in. Here's another method scope, and we have a int a is equal to 3. So in here, if we say print a plus b, and down here we say print a times b, we're going to get different, well, we're getting different values of a's and b's. Up here, the most local definition of b is right here, so that's 5, plus the most local definition of a is this one up here, which is 5. So this is going to print out a 10 down here. Within this scope, we have a is equal to 3. Okay, we actually have no scope of b, so this is going to give us an error. If we have a scope of b in here, if we say int b is equal to 2, then this guy would be a 6. Right? But this is a procedural language where we have just the global scope that governs the entire file that we're in, as well as local scopes that involve the individual methods or functions that live within that file. The second we get into object-oriented programming, so if I steal this slide here, all of a sudden we have kind of one more layer behind this. So let me steal this guy, and we're going to change his color. He's going to be that color, and he's going to be a little bit bigger. Like that, and then we'll send him to the back. All right, and this is global object scope. And this is where public, private, protected kind of come in, where how does the scope governed by the global scope of this object translate into other objects? All right, does that kind of make sense? Or did I just confuse it that much more? Yeah, I mean, effectively, when I first read your question, I mean, the short version of it is scopes work the same in object-oriented and procedural languages. There's no difference. You don't have to redefine how a variable scope works. The difference is that the idea of the scopes that are governed by public, private, and protected variables. So when you think of an object-oriented language, you know, where you have a class maybe up here that has a public int a is equal to 5, something like that, which means that variable is accessible not just within this class, but also within other classes that could create instances of this class. That concept never existed in procedural languages like C. So it wasn't like, oh, well, how did things work without public, private, protected? It's really the other way around, where we didn't need public, private, protected because you never had that access external to that class. It just, that wasn't something that was a thing until objects came about. All right, what other questions? Going once. Going twice. All right, I'll hang out for about another minute or two in case another question pops up. Otherwise, I will see everybody next week. Same time, same station. I think we should finish the slide set then, and then we'll see what topic I'll do for the following week. But I'm pretty sure we'll finish everything for next week. Let me just quickly flip through here. I think it's going to be evolution of Java, evolution of C#, evolution of Swift, and that'll kind of close the gap for everything, and then we'll kind of see how we arrived at our most modern languages and why they are the way they are. Okay, well, I will see everybody next week then. Take care. And I'll stop the recording and I'll post a link to the video up on the event channel or the workshop page as well. All right, take care. Bye-bye.